morning, dear students. Today's lecture is lecture number 9 and the title of today's lecture is the unbounded solution. We will be talking about a linear programming problem which has a unbounded solution. The outline of today's talk is as follows. We will first study the graphical solution of a linear programming problem which is unbounded, and then we will solve the same example with the help of the simplex method. The idea is to make a comparative analysis of the unbounded case with the help of both the methods, that is the graphical solution and the simplex solution. The conclusion will be to find out those conditions under which we can identify that a problem has an unbounded solution during the simplex calculations. After that, I will ask you a question and subsequently I will reply to that question, and finally I will give you an exercise. So, let us begin. Now, suppose we have this problem which is given to us. It is maximization of 5x1 minus x2. This is subject to two constraints of the type 2x1 plus 3x2 greater than or equal to 12, x1 minus 3x2 less than or equal to 3. Now, first of all, we will look at the solution with the help of the graphical method. So, for this we will need to plot the feasible domain. Now, first of all, we will plot the constraints. So, these are the two constraints. This is the first constraint and this is the second constraint, and now we have to decide out of all these 4 regions which is the region that is the feasible domain corresponding to the problem, and this is known by substituting the origin into the constraints, and you can see that this region is the region of interest. This is highlighted by these bold lines. So, this line and this line, these 3 lines enclose the feasible domain, and the coordinates of these vertices are A, we will call it as A0, 4, similarly B, this is 5, 2 upon 3, and this is the feasible region of the problem. Now, as you will see that this feasible region is unbounded towards the right hand side and towards the upward direction. Now, the question is, what is the solution? Although the feasible domain indicates that the feasible domain is an unbounded region, but we want to see what is the solution to the problem. So, we will need to investigate the value of the objective function at these vertices and let us see what happens. So, the family of straight lines which represents the objective function is shown here, and this can also tell or indicate that the solution has an unbounded solution. So, let us look at this table which indicates the value of the objective function at each of these points A, B, etc. So, the coordinates of A are 0, 4. If you substitute it in the objective function, that is 5x1 minus x2, you get minus 4. Similarly, if you substitute B 5, 2 upon 3, then you get 73 upon 3. Now, since these are the only 2 points of the feasible region, we want to see what happens if we take a point P on the edge, on a particular edge of the feasible region. So, let us suppose you take a point P over here on this line, on this edge of the vertex. Then this P has a value 29. If you substitute 6 1 in the objective function, 5 6 are 30 minus 1 is 29, and that is how the value of the objective function at the point P is 29. Now, suppose I take any point P on this line segment, I take any point P. What will be its coordinates? Since this point P is lying on this line segment, its general form will be of the type 3 plus 3y comma y. This will be the general form of any point which is lying on this line segment. And if you substitute this point P in the objective function 5x1 minus x2, what will you get? You will get 5 times 3 plus 3y minus y, and that comes out to be greater than or equal to 29. And we see that as and how the value of y goes to infinity, that is y, the value of y is increased, as and how the value of y increases, the value of the objective function will also increase, and this is an indication that the problem has a unbounded solution. So, this particular problem has a unbounded feasible region and the solution is also unbounded. Now, once we have done this, now let us look at the same problem with the help of the simplex method. And since there are one constraint is of the greater than type and the second constraint is of the less than type. So, now let us solve the problem with the simplex method. Now, since the problem has two constraints, one constraint is of the greater than type and the second constraint is of the less than type, therefore, we will need to use artificial variables, and we can use the two phase method to solve this problem. So, first of all, let us convert this problem into the problem in the standard form. The problem in the standard form looks like this: maximization of 5x1 minus x2 subject to twice x1 plus 3x2 minus x3 plus x5 is equal to 12, and the second constraint becomes x1 minus 3x2 plus x4 is equal to 3. Now, this problem has been converted into the problem in the standard form, and since this artificial variable x5 has been introduced, so we will use the two phase method, and in the first phase we are going to maximize minus x5, because the phase 1 says minimization of some of the artificial variables, or in other words maximization of minus x5, maximization of all the artificial variables. So, the constraints are as before, only thing is the original objective function has been set aside for the moment and it has been replaced by a temporary objective function, that is maximization of minus x5. So, let us write down the table. The first phase initial table looks like this. The bases are as follows, that is x5 and x4, and their corresponding values in the objective function are minus 1 and 0. x1 entries are 2 1, x2 entries are 3 minus 3, x3 entries are minus 1 0, x4 entries are 0 1 and x5 entry is 1 0, and right hand side is 12 3. On the top row we have the coefficients of the objective function. X1 has coefficient 0, x2 has coefficient 0, x3 has coefficient 0, x4 has coefficient 0, only x5 has coefficient minus 1 in the phase 1. So, first thing what we need to do is we need to look at what is the BFS. In the initial table, the BFS is x5 is equal to 12 and x4 is equal to 3 and all other 0. So, what will we do? First of all, we will calculate the deviation rows, and how are they calculated? As you are very familiar now, the basic variables have entry 0. So, since 0 1 x4 variable is a basic variable, therefore, it has entry 0. Similarly, x5 is a basic variable, so it has entry 0. The other 3 entries can be obtained as before: 0 minus 1 0 multiplied by 2 1, which comes out to be 2, and similarly 0 minus 1 0 multiplied by 3 minus 3, which comes out to be 3. So, we need to take a decision which variable should enter the basis, and for this we look at the entries in the deviation rows, and we find that 3 is the maximum value in the deviation rows. Therefore, this indicates that the variable x2 should enter into the basis. So, the entering variable is x2, and then we need to perform the minimum ratio test by dividing the entries of the right hand side with the pivot column. Now, you will observe that the pivot column has minus 3 as a negative entry. So, this has to be excluded while applying the minimum ratio test, and it indicates that we have only one choice, and that is x5 should leave the basis. So, therefore, x5 should leave the basis. This indicates that our pivot is nothing but 3. So, this is our pivot, 3 is our pivot, and we have to make this 3 as 1 and the other entry as 0. So, we have to apply the elementary row operations in such a way that 3 minus 3 becomes 1 0. So, what we should do? First of all, we will divide the first row with 3. So, here you are, R1 has to be replaced by R1 by 3, and the second elementary row operation is R2 has to be replaced by R2 plus 3 R1. With these two elementary operations, we can now look at our next table. So, phase 1 table 2, this is what it looks like. We have the two basic variables x2 and x4, and the entries are obtained like this: 2 by 3 3, 1 0, minus 1 by 3 minus 1, 0 1, 1 by 3 1, 4 15, and the corresponding BFS turns out to be x2 is equal to 4 and x4 is equal to 15 and all others 0. Then we have to take a decision as to whether the stopping condition has been satisfied or not. We calculate the deviation entries and we find this turns out to be 0, 0, 0, 0 and minus 1. This indicates that the stopping condition has been satisfied, and therefore, phase 1 is completed. So, this tells us that the phase 1 has been completed, and this corresponds to the point A in the graphical solution. Phase 1 is completed and it corresponds to the point A in the graphical solution. Let us look at the graphical solution. This solution is telling us that it is 0, 4. So, let me go back to the graphical solution. Yeah. here it is. So, this point A 0, 4 we have obtained at the end of phase 1, right. Next, what we need to do is we need to look at the phase 2. So, for phase 2 what we have to do is we have to bring back the original objective function into the problem, and this will be incorporated by entering the top row in the table. So, phase 2 table 1 will look like this: 5 minus 1, 0 and 0, and x1 entry, x2 entry, x3 entry and x4 entry. You will notice that the x5 entry is not shown here in this table. The reason is that x5 was an artificial variable, and in the end of the previous phase 1 we have seen that x5 has become 0. At the end of the phase 1 table 2 we have seen that x5 has disappeared from the basis. So, x5 is actually 0. Therefore, we can drop this x5 variable and move to the phase 2. So, the phase 2 is having the same BFS as the end of the phase 1, and this is the basic feasible solution. x5 is equal to 4 and x4 is equal to 15 and all others 0. So, let us calculate the deviation rows, and we find that the deviation rows are as follows: 5 minus 1 0 multiplied by 2 by 3 3, which turns out to be 17 by 3, then minus 1 multiplied by minus 1 0 multiplied by 1 0, which comes out to be 0. Anyway, this is a basic variable, so its entry will be 0. Similarly, x4 is a basic variable, so its entry will also be 0. We need to calculate the entry corresponding to x3, which turns out to be 0 minus 1 0 multiplied by minus 1 by 3 minus 1, which turns out to be minus 1 by 3. This indicates that only this entry corresponding to x1 is positive, and this shows that x1 variable should be the entering variable. So, our x1 should enter the basis, and similarly we will perform the minimum ratio test 4 upon 2 by 3 and 15 upon 1, and this tells us that our leaving variable is x4. So, what is the pivot? Yes, the pivot is 3, this 3 entry is the pivot, and we need to apply the elementary row operations in such a way that this column becomes 0 and 1. So, what are the two elementary row operations that we should use? First of all, we will make this entry 3 as 1, and this can be done by dividing the entire row by 3. Therefore, we will apply a elementary row operation. R2 has to be replaced by R2 by 3, and similarly we will apply another elementary row operation. R1 should be replaced by 2 by 3 R1 minus 1. So, this means that this entry will become under x1 column will become 0 and 1, and this is the resulting table 2 for phase 2. Our entry under the x1 column has become 0 and 1, and similarly under x2 it has been 1 0, x3 is minus 5 by 9 minus 1 by 3 minus 1 by 9 1 by 3, and the right hand side becomes 2 by 3 and 5. Now, we need to calculate the deviation entries, and we find that the deviation entries are 0, 0, 10 by 9 and minus 16 by 9. The BFS at this table at this stage is nothing but x2 is equal to 2 by 3 and x1 is equal to 5 and all others zeros. Now, you will observe that this particular point 5 comma 2 by 3 is nothing but the point corresponding to B in our graphical solution. So, B is the point 5 comma 2 by 3. This is the point in the graphical solution that we have seen. Let us just go back and see B 5 comma 2 by 3 in the graphical solution. Here it is B 5 comma 2 by 3. So, in the first iteration we got A 0 comma 4, now we have got B 5 comma 2 by 3. So, therefore, let us now look at what we have to do next. We have to see which variable should be the entering variable. So, the entering variable is nothing but the variable x3, because the entry corresponding to x3 variable in the deviation rows is positive only for the x3 variable. Also, the leaving variable has to be decided, but what do you find? You find that all the entries in the pivot column, that is under x3, they are negative. How do you see that? This is minus 5 by 9, this is negative, this is minus 1 by 3, this is negative. So, you just cannot apply the minimum ratio test, because as you know that the minimum ratio test has to be applied only for entries in the pivot column which are positive. But here we do not have any positive entries, and therefore, the minimum ratio test cannot be applied. The minimum ratio test cannot be applied, and therefore, the leaving variable cannot be decided. So, the minimum ratio test has failed, and therefore, this is an indication that the problem has a unbounded solution. And in fact, this is what we were looking for. So, the condition to identify in the simplex calculations whether a given problem has a unbounded solution or not is this, that is, if the minimum ratio test fails due to all entries in the pivot column either 0 or negative, then this indicates that the problem has a unbounded solution. So, we can conclude that if the minimum ratio test fails, then it can be concluded that the problem has a unbounded solution. That is, all the entries in the pivot column are either 0 or negative. Also, there could be a situation where the right hand side is 0. This situation is called cycling, which I have not included in this particular lecture. So, with this condition now we have a question in front of us, and the question is it possible for an LP to have a unbounded feasible domain and at the same time have a fixed objective function value or a finite objective function value? So, you can just think about this whether it is possible or not, because there are two things. One is the feasible domain is unbounded, and the second thing is the objective function value goes on to infinity, as we have seen in the previous example. But at the moment I am asking you, is it possible that LP has a unbounded feasible region and at the same time its objective function value is finite, that is, it does not go to infinity, and in fact it becomes fixed. The answer to this is yes. The answer to this is yes. This can be seen in this example, maximization of 6x1 minus 2x2 subject to x1 minus x2 less than or equal to 1, 3x1 minus x2 less than or equal to 6 and x1 and x2 both greater than or equal to 0. Now, what is the meaning of this problem? Let us look at it graphically. So, first of all, we will try to draw the two constraints so that we can see what the feasible domain looks like. So, first constraint, this is what it looks like, and we have to decide whether the feasible domain is above the line or below the line, and we find that the feasible domain is above the line, which is indicated by the arrow. Then we plot the second line. So, here is the second constraint, and then we decide whether the feasible domain is above the line or below the line. This we determine by substituting the origin into the constraint, and we find that the feasible domain is above the line. Now, this indicates that our feasible region is bounded by these line segments. First of all, this line segment, second line segment, third line segment and fourth line segment. So, this is the feasible region of the problem, and we can shade this feasible region to indicate that this is unbounded towards the vertical direction, upward vertical direction. Also, we need to look at the vertices of this feasible region. The first vertex is O, that is the origin, then we have A, then we have B, and let us look at the family of straight lines which represents the objective function. Now, we will evaluate the objective function at each of these points O, A, B. So, here you see O is the origin. So, the objective function value is 0. The point A is 1, 0 and its value is 6. Similarly, at B the point is 5 by 2, 3 by 2, its value is 12, and in fact what you find that suppose you take any point P on the line segment as indicated in the figure, its value will also be 12. Now, how to determine this? This can be determined by looking at the general formula for a point P on this line segment. Because it satisfies this particular constraint, therefore, this point P has the coordinates t, 3t minus 4, where t goes to infinity. And if you substitute this point P into the objective function, you will get a value 12, and this indicates that for all points lying on this edge BP, all points on this line segment BP will have a constant value 12. This indicates that the problem has a unbounded feasible region, but the objective function value is not infinite, it is finite and it is fixed. It is fixed equal to 12, and this is also indicated by the family of straight lines which represents the objective function. In fact, you can see that the problem has multiple solutions. Why it has multiple solutions? It has multiple solutions because the slope of the objective function is the same as the slope of the constraint. This you could have seen by looking at the problem itself. See, 6x1 minus 2x2, this, the slope of this objective function is the same as the slope of 3x1 minus x2 less than or equal to 6, and this is an indication that the problem has multiple solutions, but it also has a feasible domain which is unbounded. So, therefore, this beautiful example illustrates that a problem may have unbounded feasible domain, but the objective function value could be finite. So, now I will give you an example to solve. So, please solve this example later on. Maximization of 3x1 plus 2x2 subject to 2x1 plus 3x2 less than or equal to 9, x1 minus 5x2 less than or greater than or equal to minus 20. Now, the hint for solving this problem is you have to take care of this negative sign. The right hand side is negative, and as you know that for solving an LP, the right hand side should be positive. So, you have to convert it into the positive sign by multiplying it with the negative sign. Thank you.